All right, welcome to the deep dive. We flip a switch, our lights come on, we charge our phones, we pretty much take electricity for granted. But have you ever thought about all the stuff that has to happen to make that seemingly simple act possible? Today, we're going to dive into the world of power substations. Those installations that most of us drive by every day without giving them a second thought.
Yeah, they're kind of these silent giants of the electrical grid, quietly doing their job behind the scenes.
Exactly. And you've actually provided us with a really interesting and comprehensive set of sources about this topic. So we're going to take a deep dive into all that information and try to pull out the most important and fascinating details for you. Think of it as a crash course in power substation essentials without getting bogged down in all the super technical jargon.
Yeah, we'll skip all the complex equations and focus on the core concepts and why they matter. By the end, you'll have a much clearer picture of what these installations are, how they function, and why they're so critical for our modern lives.
Right. So we've got research papers, articles, technical specifications, even some practical application examples, a really good mix. So let's jump right in. First things first, got to make sure we're all on the same page. What exactly is a power substation?
Okay, so the sources we have define a power substation as basically a collection of electrical installations, equipment, and associated gear, usually operating at medium or high voltages. And they're specifically designed for a bunch of key tasks: protection, measurement, maneuvering, and transforming electrical quantities.
Yes, it sounds like they're like these hubs where electricity gets managed and controlled and sent where it needs to go.
Exactly. Every bit of electricity that we use, every single watt, passes through at least one substation on its journey from where it's generated to where it's actually consumed.
Huh. And I guess that's why the sources emphasize that substations play a crucial role in the power system, or as they call it, the SE. Seems like shutting down a substation can have huge consequences for the economy.
Yeah, they're not just passive components. If a substation goes offline unexpectedly, it can really disrupt things. Factories might have to stop production, businesses might lose power, even transportation systems can be affected.
Right. They really are essential infrastructure. So what are some of the main things that substations do beyond just moving electricity around?
Well, they perform a bunch of functions, monitoring electrical quantities for things like control, protection, and automation, basically keeping tabs on the whole system. They also provide operational resources to support the broader electrical grid, like voltage regulation and reactive power compensation.
Voltage regulation. That sounds important.
It is. They make sure that the voltage levels are correct for both the long-distance transmission lines and for the lower voltage distribution systems that feed power to our homes and businesses. And they also adjust the voltage depending on the load demands, so your lights don't dim every time your neighbor turns on their hairdryer.
Makes sense. And then some substations can even handle energy conversion, right? Like with DC transmission systems.
Absolutely. For very long-distance power transmission, using high-voltage direct current, HVDC, is more efficient. So substations might include specialized equipment to convert the electricity from AC to DC, transmit it over a long distance, and then convert it back to AC at the other end.
So it's like translating the electricity into a different language for its long journey. All right, so we've got a basic idea of what a substation is and why they matter. Now, let's dig into how they're categorized. Seems like the sources mention several ways to classify these installations.
Yeah, we can look at them based on their primary function, the type of installation, like whether they're indoors or outdoors, and the voltage level at which they operate.
Okay, let's start with function then. What different roles do substations play within the power system?
Well, you have elevating substations, and these are typically located right next to power generation plants. Their main job is to increase the voltage of the electricity being generated.
Why do they need to boost the voltage right away?
For long-distance transmission, it's much more efficient to transmit electricity at a higher voltage. By stepping up the voltage, you can dramatically reduce the amount of current flowing for the same amount of power, which helps to minimize energy losses during transmission. Think of it like using a smaller pipe to transport the same amount of water but at a higher pressure.
So it's all about reducing losses over those long transmission lines. Makes sense. And then what happens when that high voltage electricity gets closer to where people actually need to use it?
Well, that's where lowering substations come into play. These substations are typically located closer to urban areas or industrial centers. Their role is to decrease the voltage of the electricity coming from the transmission lines down to a safer and more manageable level for local distribution.
So it's like stepping down the pressure in the water pipe before it goes to individual houses.
Exactly. And then we have distribution substations, which take that reduced voltage and route it down even further to what's called the primary distribution level. This is the voltage level that's used to supply power to smaller areas like neighborhoods or industrial parks.
Got it. So it's kind of a cascade. High voltage for long distance travel, then step down again for local use. Now, what about switching substations? What do they do?
Switching substations are primarily focused on connecting different electrical circuits together, often at the same voltage level. Their main purpose is to provide operational flexibility for the power grid.
So they're like the traffic controllers of the electricity highway.
Yeah, sort of. They allow grid operators to reroute power flow as needed, to add or remove sections of the grid for maintenance or repairs, or to isolate a faulty section to prevent further damage or blackouts.
Huh. I never thought about how they actually managed to do maintenance on these high voltage lines without shutting down the entire system. Okay, and then the last category the sources mentioned is converter substations.
Right. These are specifically associated with HVDC transmission systems. They handle the conversion of electricity between AC and DC. Rectifier substations convert AC to DC at the sending end, and inverter substations convert DC back to AC at the receiving end.
Fascinating. So it's like they temporarily change the electricity's format for more efficient travel. Okay, so that covers function. What about the different types of installations?
Well, the most straightforward one is the outdoor substation. As the name implies, all the equipment in these installations is out in the open, exposed to the elements.
So they need to be pretty rugged to handle all kinds of weather conditions.
Definitely. Rain, snow, ice, extreme heat, they have to withstand it all. And that often means more frequent maintenance and inspections are needed compared to installations that are protected from the weather. Figure 2 in the sources actually gives a good visual of a typical outdoor substation. You can see all the equipment like transformers and circuit breakers out in the open.
Right. And then, in contrast, we have sheltered substations.
Yeah, in these installations, the equipment is housed within some sort of building or enclosure to protect it from the elements. This obviously reduces wear and tear and can extend the lifespan of the equipment.
Makes sense. And figure 3 shows an example of a sheltered substation, right?
That's right. You can see that the equipment is enclosed within a structure, providing a more controlled environment. Now, another type of installation is a gas-insulated substation, or GIS.
I've heard of those. They sound pretty advanced.
They are. In a GIS, all the electrical equipment is completely sealed inside compartments that are filled with an insulating gas, typically sulfur hexafluoride, or SF6. This gas has amazing properties for quenching electrical arcs, making GIS very safe and reliable.
And because everything is sealed up, they can often be much smaller than traditional substations, right?
Exactly. That's a big advantage, especially in urban areas where space is limited. Figure 4 shows a typical GIS installation. You can see how compact it is compared to the outdoor substation we saw earlier.
Definitely a lot more space efficient. And the last type of installation is a hybrid substation.
Right. Hybrid substations combine elements of both GIS and conventional air-insulated equipment. They might use GIS for the high-voltage sections where space is tight or where enhanced reliability is crucial, and then use air-insulated equipment for other parts of the installation where those factors aren't as critical.
Makes sense. It's like a best-of-both-worlds approach. All right, so we've got function and installation covered. Now, the last way to classify substations is by voltage level.
Right. Substations are grouped based on the voltage tiers they operate at, and these voltage tiers essentially reflect the different stages of the electricity's journey from generation to consumption.
So what are those different voltage levels?
You have extra high voltage, EHV levels, which are used for the long-distance bulk power transmission lines, and then distribution voltage levels, which are used to distribute power to regional areas and local substations, and finally, low voltage levels, which is the voltage that's delivered to homes and businesses.
Makes sense. And I noticed the sources mention specific regulations that apply to different voltage levels, things like NR 14039 and NR 5430. What are those?
Those are Brazilian regulatory standards that set safety and operational guidelines for electrical installations. NR 14039 focuses on medium voltage installations, and NR 4410 deals with low voltage installations.
So these voltage levels aren't just arbitrary. They're tied to specific safety and operational standards. To know. Okay, we've got a solid foundation now in terms of the types and classifications of power substations. Now let's get into the nitty-gritty, the actual equipment that you'd find inside one of these installations.
All right. Think of it as an orchestra of electrical components, each playing a specific role to keep the music of the power grid flowing smoothly.
I like that analogy. And first up in our equipment tour, we've got lightning arresters. Sounds pretty self-explanatory.
Yeah, the name pretty much says it all. Their main job is to protect the substation equipment from those sudden and very intense surges in voltage that can happen during a lightning strike.
So they're like the bodyguards for the electrical system.
Exactly. They're usually placed at key entry points in the substation, like where transmission lines come in or near transformers. They're designed to provide a path of least resistance for the massive electrical surge from a lightning strike to flow safely to the ground, rather than going through the substation equipment and potentially causing damage. Figure 6 in the sources shows some common locations for lightning arresters.
Makes sense. So they're strategically positioned to intercept those surges before they can wreak havoc. How do these lightning arresters actually work, though? What are they made of?
They typically use nonlinear resistors. Older designs often use silicon carbide elements with spark gaps, but the more modern ones use metal oxide varistors, usually made of zinc oxide or ZNO. These newer types tend to have better performance and longer lifespan.
Interesting to see that technological progression. And I noticed the sources mentioned different classes of arresters as well. What's the distinction there?
Yeah, they're classified based on the size of the substation or the equipment they're protecting and how much surge current they can handle. You have station class arresters for large substations, intermediate class for smaller substations and lines, and distribution class for even smaller distribution substations.
Got it. So, bigger substation, bigger arrestor. Now, moving on, we have disconnect switches. These also sound like they have a pretty obvious function.
Yeah, they're essentially big, manually operated switches that are used to isolate sections of the substation equipment or the entire substation from the rest of the power grid.
Sounds pretty straightforward.
It is, but there's one very important thing to remember about disconnect switches. They should only be operated when there's absolutely no current flowing through the circuit they're connected to. Unlike circuit breakers, which we'll talk about later, they are not designed to interrupt current flow. Trying to open a disconnect switch under load could result in a very dangerous electrical arc. Figure 7 shows what a disconnect switch looks like.
So they're like the big, heavy-duty on-off switches, but you have to make sure the power is completely off before you flip the switch.
Exactly. Their primary function is to provide a visible and guaranteed isolation point. You can actually see the gap in the circuit. This is crucial for safety during maintenance or repairs because you want to be absolutely sure that the equipment is completely isolated from any source of electrical energy before anyone starts working on it.
Right. Safety first. So besides that main isolation function, are there other uses for disconnect switches within a substation?
Oh yeah, they're pretty versatile. They can be used to bypass equipment that needs to be taken out of service for maintenance without interrupting the power flow to the rest of the system. They can also be used to transfer circuits between different bus bars within the substation, which are like the main electrical highways that distribute power. And some specialized types can even provide a means for safety grounding of isolated equipment.
So they're like the multi-tool of substation operations. And I see there are quite a few different types of disconnect switches based on their physical design and how they open and close. Lateral, vertical, pantograph. What are all those about?
Yeah, there's a whole family of disconnect switches. Figures 9 through 16 show some of the common types. The choice of which type to use often depends on things like the available space within the substation, the voltage level, the amount of current it needs to handle, and whether it's operated manually or by a motor. There are also specific industry standards that apply to their design, like ABNT, NBR, IEC 62271-102.
It sounds like choosing the right disconnect switch is more involved than I initially thought. Okay, so next up we have potential transformers, or TPs. These seem to be all about measuring voltage, but in a safe way.
Exactly. You're dealing with very high voltages in a substation, so you can't just directly connect a regular voltmeter to a high voltage line. That would be extremely dangerous. And the voltmeter wouldn't be able to handle that much voltage anyway, so that's where potential transformers come in.
They're like the step-down converters for voltage measurement.
Exactly. They take that very high voltage and step it down to a much lower, safer, and easily measurable level. And this lower voltage signal can then be used by all sorts of instruments and protection devices in the substation without any risk of damaging them or endangering personnel. Figure 18 shows a typical potential transformer.
So they're like the translators for voltage. making it understandable for our monitoring equipment. What are some of the devices that actually use these lower voltage signals?
Oh, all sorts of things. Voltmeters to display the voltage level, voltage relays that are part of the substation's protection system, and even the voltage coils within energy meters that measure electricity consumption.
Okay, so they're pretty crucial for monitoring and controlling the substation. How are these potential transformers actually built? Do they use the same principles as those big power transformers we talked about earlier?
Yeah, they're similar in that they use electromagnetic induction, but on a much smaller scale. A typical potential transformer has a primary winding with a lot of turns of wire and a secondary winding with fewer turns. The ratio of these turns determines the voltage reduction ratio. And the secondary voltage is usually standardized to UN15V, or UN15, divided by the square root of 3 volts. Figure 19 shows a schematic diagram of a potential transformer.
So they're like mini transformers, specifically for voltage measurement. You mentioned that they use electromagnetic induction. Are there other types of potential transformers that use different principles?
Yeah, for very high voltage levels, you often find capacitive voltage transformers, or CVTs. Instead of just using windings, they incorporate capacitors to help step down the voltage. They tend to be more cost-effective for those very high voltage applications. Figure 22 shows what a CVT looks like. And interestingly, they can also be used for something called power line carrier communication.
Power line carrier communication. What's that?
It's basically a way to transmit voice or data signals over the high voltage power lines themselves. The CVTs act as the interface between the communication equipment and the power lines.
Huh. That's pretty clever. So it's like sending a secret message along with the electricity. What are some of the important electrical characteristics that you need to consider when selecting a potential transformer?
Accuracy is really important, especially if the TP is being used for revenue metering, where you need very precise measurements to accurately bill customers for their electricity usage. They have different accuracy classes depending on how precise they need to be. The load connected to the secondary side of the TP, called the burden, can also affect the accuracy, so that needs to be considered as well. And of course, there are industry standards that govern their design and testing, like NBR 6855 for inductive TPs and IEC 670600445 for capacitive ones. Tables 4 and 5 show some examples of typical TP specifications.
Okay, lots of technical details to consider. So we've got voltage covered. Now, what about measuring current?
That's where current transformers, or TCs, come in. They perform a similar role to potential transformers, but for measuring current instead of voltage.
Right, because you can't just slap an ammeter onto a high current line either.
Exactly. It would be unsafe and the ammeter wouldn't survive. So current transformers step down the high current to a much lower and safer level that can be easily measured and used by instruments and protection relays. Figure 23 shows a variety of current transformers.
So they're essentially doing the same thing as potential transformers, but for current. What kind of equipment uses these lower current signals?
Primarily energy meters to measure electricity consumption and protection relays to detect overcurrents and faults in the system. The relays constantly monitor the current, and if it goes above a certain threshold for a certain amount of time, they'll trip a circuit breaker to isolate the fault.
Makes sense. So similar function to TPs, but for current. What about different types of current transformers? The sources mention quite a few based on their design and construction.
Yeah, there's a whole range of designs. You have wound type, where the primary winding is made of multiple turns of wire. Bar type, where the primary is just a single bar that passes through the core. Window type, which has an opening for the primary conductor to pass through. Bushing type, specifically designed to fit around bushings on high voltage equipment. And even split core types, which are really handy because you can install them around an existing conductor without having to disconnect it. Figures 26 through 32 show these different types.
Wow, so many variations. I guess the choice of which type to use depends on the specific application and the physical constraints of the installation.
Exactly. Key things to consider when selecting a TC are the nominal voltage and current, the short circuit current rating, the accuracy class, and the required insulation levels. Tables 6 and 7 show examples of typical specifications. And of course, there are industry standards that apply here as well, like ABNT, NBR 6856, and IEC 6000441. Table 8 actually lists some common standard current ratios for TCs.
Lots of technical details to keep in mind. All right, moving right along in our equipment tour, we come to circuit breakers, or disjuntors. These seem like the real muscle of the substation when it comes to interrupting the flow of electricity.
Absolutely. They're the heavy hitters, the ones that actually physically break the circuit when a fault is detected or when you need to de-energize a section of the substation for maintenance. Figure 33 shows a typical circuit breaker.
So they're the ones that actually stop the flow of electricity. How do they manage to do that safely, though, especially when dealing with such high voltages and currents? I mean, you don't want to create a massive explosion every time you need to interrupt the flow.
That's a good point. Interrupting a high-power circuit is not a trivial task. There's a lot of energy involved. That's why circuit breakers have specialized mechanisms for what's called arc quenching. When the breaker's contacts separate to interrupt the current flow, an electrical arc forms, and this arc needs to be extinguished very quickly to prevent damage to the breaker and ensure a safe interruption.
Arc quenching sounds intense.
It is, and there are different types of circuit breakers based on how they extinguish that arc. Some of the older ones used oil to quench the arc, while others use compressed air. But the most common ones nowadays, especially for high-voltage applications, use a special gas called sulfur hexafluoride, or SF6. It's really good at quenching arcs and is non-toxic.
So SF6 is the go-to gas for these high-power circuit breakers.
Yeah, it's pretty much the industry standard now. And for lower voltage applications, you often find vacuum circuit breakers. As you might guess, they use a vacuum to help extinguish the arc. Table 9 in the sources actually provides a nice comparison of the different types of circuit breakers.
Interesting to see the different approaches. What are some of the main parts that make up a circuit breaker regardless of the quenching mechanism they use?
Well, they've all got conducting parts that carry the current when the breaker is closed, insulating parts to keep everything electrically isolated, the arc extinguishing system, the operating mechanism that provides the force to open and close the contacts, and various control and monitoring components. Some might have extra features like pre-insertion resistors to limit voltage surges during switching or synchronizing devices to ensure smooth operation.
Sounds like a complex piece of machinery. And when you're specifying a circuit breaker for a particular application, what are some of the key things you need to consider?
Lots of factors. The voltage and current rating, the short circuit current interrupting capability, basically how much current it can safely interrupt without being damaged, the insulation level, the type of arc quenching medium, the type of operating mechanism, whether it's spring operated, hydraulic, or pneumatic. And of course, there are relevant industry standards to follow, like the IEC 62271 series.
Table 10 shows an example of a circuit breaker specification. Lots of numbers and details there. Okay, on to the next big player. Power transformers, or transformadores de potencia. These seem like the heart and soul of the AC power system.
They absolutely are. Power transformers are what make it possible to efficiently transmit electricity over long distances and distribute it at various voltage levels to meet the needs of different users. They're based on the principle of electromagnetic induction, essentially using magnetic fields to transfer energy between two or more coils of wire without any direct electrical connection. Figure 34 shows a massive power transformer, and Figure 35 shows the basic concept of how they work.
Right. They're the voltage and current shifters, stepping up the voltage for efficient transmission and then stepping it back down for distribution and use. What are the main parts that make up a power transformer?
Well, at the core, you've got windings, which are usually made of copper, and a core, which is typically made of laminated silicon steel. The windings carry the current and create the magnetic fields, and the core helps to guide the magnetic flux. These windings and the core are what we call the active part of the transformer.
And then there are a bunch of accessories as well, right?
Exactly. You have bushings, which provide those insulated connections between the windings and the external circuits, a cooling system, because these transformers can generate a lot of heat, and various protection devices like pressure relief valves and temperature sensors. Figure 36 shows the main parts of a power transformer.
Cooling sounds important, especially for those really big transformers. The sources mention terms like ONAN and ONAF. What are those?
Those are standard abbreviations for the different cooling methods used in oil-immersed transformers. ONAN stands for oil natural, air natural, which means the oil inside the transformer circulates naturally by convection, and the heat is dissipated to the surrounding air, which also circulates naturally. ONS stands for oil natural air forced, which means the oil circulates naturally, but fans are used to force air over the cooling fins to improve heat dissipation.
Right, so it's like having a radiator with a fan to help it cool more efficiently. And tables 12 and 13 in the sources show all those cooling method abbreviations. I see there are also different types of power transformers listed in the sources, categorized by their purpose and function.
Right. There are current transformers and potential transformers, which we've already discussed in detail. Then you have interconnection transformers, which are used to connect different parts of the power grid that operate at different voltage levels. Auto transformers, which are a special type that has a single winding with a tap and is often used for smaller voltage adjustments. Distribution transformers, which step down the voltage to lower levels for local distribution. And finally, those big power transformers that are used for high voltage transmission and at generating stations. Table 14 gives a good summary of those different types.
Okay, lots of specialized types. What are some of the important things to consider when you're talking about the electrical characteristics of power transformers?
Yeah.
I see the sources mention impedance.
Impedance is really important, especially when you have multiple transformers operating in parallel. You want them to share the load equally, and having similar impedance values helps to ensure that. It also plays a role in calculating fault currents, which are those huge currents that can flow during a short circuit.
Table 15 shows a typical specification for a large power transformer. And as you might expect, there are a ton of standards that apply to their design and testing.
Yeah, organizations like ABNT, ISO, IEC, and ANSI all have standards for power transformers. It's a very mature and highly standardized technology.
Okay, 2 more equipment categories to cover, and then we can move on to how all this stuff gets connected together. Next up are capacitor banks. What are those all about?
Capacitor banks are primarily used for what's called power factor correction.
Power factor correction. Sounds a bit technical.
It is, but the basic idea is this. AC electrical systems have 2 types of power. Real power, which is what actually does the work, like running your appliances, and reactive power, which doesn't directly do work but is needed by certain types of equipment to operate correctly. Think of reactive power as the froth on top of a beer. It takes up space but doesn't contribute to the actual beer you can drink. And this reactive power can cause problems in the electrical system by increasing current flow and losses.
Okay, so capacitor banks help to reduce that reactive power.
Exactly. They supply the reactive power locally, which reduces the amount that needs to flow from the power source, making the system more efficient. Figure 37 shows a typical capacitor bank.
They're like the reactive power sponges of the substation.
That's a good way to put it. And they can be connected in different configurations depending on the voltage and the application. Common connections include delta and Y, and there are also more specialized connections like double Y and H-bridge for larger banks or series capacitor applications. Figures 38 through 41 show some examples.
And speaking of series capacitors, I see the sources mention those briefly as well. How are those different?
Series capacitor banks are actually installed in series with the transmission lines themselves, rather than within the substation. They help to reduce voltage drops and increase the power transfer capacity of the lines, which can be especially beneficial for long transmission lines.
Interesting. So they're like adding a booster pump to the water pipe to help it flow more easily. Okay, and last but not least, in terms of major substation equipment, we have reactors or reators.
Reactors are basically coils of wire with either an air core or an iron core, and their primary function is to limit or control the flow of current in the system, typically by absorbing reactive power. Figure 42 shows a reactor.
So they're kind of like the opposite of capacitor banks.
In a way, yes. Capacitor banks supply reactive power while reactors absorb it, but they both play important roles in maintaining the stability and quality of the power supply.
And what are some of the main applications for reactors?
They're used as fault current limiters to reduce those huge currents that can flow during a short circuit, protecting equipment from damage. They can be used as inrush current limiters to protect equipment when it's initially energized. They're used in harmonic filters to improve power quality. And they can also be used for voltage control and reactive power compensation. Sounds
like they're the jack of all trades of the substation world. And as you might expect, they're also covered by various industry standards like IEC 57.21 and IEC 60766.
Yeah, everything in a substation is designed and built according to very specific standards to ensure safety and reliability.
Okay, we've gone through a whole bunch of individual pieces of equipment. Now let's talk about how it all gets connected together. The sources mentioned different busbar configurations. What exactly are busbars, and why are there different ways to arrange them?
Busbars are essentially the main electrical highways within a substation. They're typically made of copper or aluminum bars and are responsible for distributing power to all the different circuits and equipment within the substation.
So they're like the main power distribution network within the substation.
Exactly. And the way these busbars are arranged, the configuration, has a big impact on the reliability and cost of the substation.
Okay, so what are some of the common configurations and what are the trade-offs involved?
Well, the simplest one is the single bus configuration. This is where all the circuits are connected to a single bus bar. Figure 43 shows this arrangement. It's the least expensive and requires the least amount of space, but it's also the least reliable.
Why is it less reliable?
Because if there's a fault on the bus bar itself, or if you need to take a circuit breaker that's connected to the bus bar out of service for maintenance, you potentially have to shut down all the circuits connected to that bus bar. It's a single point of failure.
Ah, I see. It's like having all your eggs in one basket. What about the single bus with bypass configuration? How does that improve things?
By adding bypass switches around each circuit breaker, you can isolate a single circuit breaker for maintenance without having to de-energize the entire bus bar. So it adds a bit more flexibility. Figure 44 shows this, but you still have that vulnerability of a single bus bar fault.
Right. Still a single point of failure. So what's the next step up in terms of reliability?
The main and transfer bus configuration. Figure 45 shows that arrangement. This uses two bus bars, a main bus and a transfer bus. Circuits can be switched between the two buses using disconnect switches, and there are bypass switches as well. So you can take a circuit breaker out of service for maintenance without interrupting power to the associated circuit, and you also have some redundancy in case of a bus bar fault.
So it's more complex, but also more reliable. What about a double bus with a single breaker configuration?
That arrangement, shown in Figure 46, offers even higher reliability. Each circuit is connected to both bus bars through a single circuit breaker. So if one bus bar fails, the circuits can be switched over to the other bus bar, and you don't lose power.
Ah, okay, so double the bus bars, double the reliability. What about a double bus with double breakers?
That's the ultimate in reliability. Each circuit has its own dedicated pair of circuit breakers, one connected to each bus bar. So even if a circuit breaker fails, you still have another one to keep the power flowing. Figure 47 shows that. But of course, it's also the most expensive option and requires the most space.
Makes sense. You pay a premium for that ultra-high reliability. Now, what about this breaker and a half scheme? That's a rather unusual name.
Yeah, it's a bit of a mouthful, but it's actually a very common configuration for high-voltage substations. It uses 3 circuit breakers to connect 2 adjacent circuits to the 2 bus bars. It's illustrated in Figure 48. This arrangement provides really good reliability because a single fault on a bus bar or a single circuit breaker failure typically only affects one circuit, leaving the other one operational.
So it's kind of a compromise between cost and reliability.
Exactly. It's not as expensive as the double breaker scheme, but offers a significant improvement in reliability compared to some of the simpler configurations. And your sources mention that it's often mandated for high-voltage substations in Brazil, referencing the ONS grid procedures.
All right. And the last one we need to cover is the ring bus configuration.
Right. In this scheme, the bus bars form a closed loop or ring, and circuits are connected to the ring via circuit breakers. It's shown in Figure 49. This configuration offers high reliability because a fault on one section of the room usually only isolates that section, leaving the rest of the ring operational. But maintenance can be a bit tricky because you have to carefully plan how to isolate a circuit breaker for work without compromising the redundancy of the ring.
Interesting. So lots of options for how to connect everything together, each with its own set of pros and cons. Okay, we've covered the main power equipment and how it's all laid out. Now let's talk about the systems that protect this equipment from.